When you plot your data, you can look for signs of a flipped graph. So for example, you plot your graph, it looks like this. Your partner plots his graph, it looks like this. You'll stare at the two plots and go, we screwed up, till you read your axes and realize, no, you've just done the reciprocal. So we've got a narrow straight line behavior here, and our asymptote looks like that. This spring is reaching a maximum length, and it doesn't seem like it's planning to go beyond that length. It's going to break. On this one, the straight line behavior is here, and the asymptote goes this way, because again, there is a distance this way, beyond which the spring is not stretching. So you're seeing the same data. This is very common.
Mr. Gillespie, please call extension 258. Mr. Gillespie.
Even if you and your partner don't make this mistake, count on a spreadsheet to doing it. The spreadsheets are very poor for doing science graphs, and they will often randomly assign an X or a Y value on the graph, and so you may have to go back in and fix it. So again, pay attention to the meaning of the graph so you can spot this error. It's extremely common error. Okay, now we'll go back to interpreting the graph when it's plotted this way. As we increase the force this way, the spring obliges us and gets longer. So the force goes up, the spring stretches to here. But as the force continues to grow upwards, the same amount, the spring is stretching less. And this failure to stretch means it's reaching the breaking point. And anyone who's grabbed a stick and tried to bend it till it breaks knows what I'm talking about. You pull, you pull, you pull, you pull, and then it just starts to really fight you. And then you just give it that one more good shove and it breaks. That is your elastic limit. So we have a breaking point is going to occur at about this stretch length. Okay. How do we use this data? Well, an engineer is going to use it to set the safe limit on building a bow and arrow, a spring-loaded shooting gun, shock absorbers on a car. They want to stay in the elastic zone. So the engineers do a test, and they find that there's a spring. I just made these numbers up. By the time it stretches 5 meters, which is a heck of a big spring, it fails somewhere between 10,000 and 15,000 newtons. So 1,000 to 1,500 kilograms, it stretches 5 meters and snaps. So the graph would look something like this. At the 5 meter limit, the spring is no longer stretching. And that occurred somewhere between 10,000 and 15,000 newtons of force, 10 to 15 kilonewtons, the spring ruptured. So we've got a distinct length where it just seems to fail at, but we've got a range of forces. Because if you see, since the distance isn't getting any longer here, it's really hard to tell when you've hit that zone for certain that we're at the limit of the spring now. It's going to break. So it looks like maybe here at around the 4 meter mark, we begin to enter our nonlinear behavior. So this zone here would represent our caution zone, and this is our like red line. Don't go past that. You're going to have a bad thing happen. Makes sense then that we would give a report saying do not stretch this past 4 meters, and then you see this on the label. This spring is rated for 10 kilonewton load, maximum deflection 4 meters. It's processes like this that allow the engineers to set their limit. Now, should we go to 4 meters? Should we go to 3? That may be the difference between their platinum and their silver line, right? They might decide for the really good ones that they've redesigned it so the springs aren't stretched past 3 meters, or they give you a spring good for 8 meters and you get a more rugged, say, suspension in your truck. That's where the artistry sort of kicks in, and the laws of the country. This factor of safety is considered a good engineering principle, and there are governing bodies that control it and variety of standards on this safety factor designed. So they have factors of safety, design safety, margin of safety, reserve factor, and this is what the engineers use. So scuba tanks, they must be stretchy to a point. If the scuba tanks stretch too much during pressure testing, it means the walls are weakening. If it fails to stretch at all, then it means the tank has been stretched out and it's reached its elastic limit. The metal is now entering a brittle phase and it may blow up. So what they do for testing every 5 years in a scuba tank, they immerse it in water and fill it with water, not gas. Gas would blow the things to pieces. They pressurize it and they watch how much the water level climbs in the tank. And there's a zone. You want slightly stretchy, not too stretchy, not too stiff. And then they rate the tank for further use. One thing that could go wrong with the tank is, let's say it was exposed to extreme heat one day, like in a fire. You took it out, it got cooled down really quickly that night, the metal could get brittle. Somebody one day decided they wanted to do a really long dive and convinced a guy to send it from 3,000 psi to 5,000 and stretch the tank out. You'd never see it by. It goes in for its next test, and they go, "Hey, the metal's not moving. It's reached its elastic limit. It will burst if it's refilled." And this is mandatory by law because one of these tanks would kill lots of people if it blew up. Okay, and you can watch the videos, and then we'll look at what engineers do. Or we did force over distance. In engineering school, they call it stress and strain. So get used to slight changes in terminology and graph axes as you go.